Hi, hello friends, welcome to our channel Study of Mathematics. Next, we will go to another problem in the same exercise. We will go section 3. First problem. Problem is if a equal to diagonal of a1, a2, a3, then for any integer n greater than or equal to 1, show that a power n equal to diagonal of a1 power n, comma, a2 power n, comma, a3 power n. This is our given problem. In this problem, we have to given a matrix, we have to show a power n matrix. But for showing this solution, we can use the procedure of principle of mathematical induction method. First, we know in starting diagonal of a1, a2, a3 means the diagonal elements are 3 elements. The given matrix has 3 by 3 matrix and the diagonal elements are a1, a2, a3. The remaining elements are zeros. For that, we have to write down the first solution. Given matrix is A equal to diagonal of a1, a2, a3. This is a diagonal element. Then this can be written as a equal to diagonal of a1, a2, a3 means a1 0 0 0 a2 0 0 0 a3. This is a diagonal of a1, a2, a3 meaning. This is 3 by 3 matrix. We have the 3 diagonal elements. Then the order is 3 by 3. Then this problem can be solved by using the principle of mathematical induction. By using principle of mathematical induction. Mathematical induction method. By using mathematical induction method, first consider for mathematical induction, first consider P of n. Then we have to prove P of 1, and then we can assume P of k, and then similarly we can prove P of k plus 1 terms or true for P of n. Then the P of n value is true. Then for that, let us consider P of n is equal to such that a power n equal to diagonal of a1 power n, comma, a2 power n, comma, a3 power n. That means a power n is equal to, the matrix is a1 power n 0 0 0 a2 power n 0 0 0 a3 power n. Next, we can true for n equal to 1. Then if n equal to 1, then P of 1 such that a power 1 equal to a power 1 1 0 0 0 a2 power 1 0 0 0 a3 power 1. That is P of 1 such that a power 1 value a equal to a1 power 1, a1 0 0 0, a2 0 0 0, a3. This is A. The given matrix A is also that, then P of, we can conclude P of n is true for n equal to 1. If P of n is true for n equal to 1, then we can assume that, suppose that the given statement P of n is true for n equal to k, that is k less greater than or equal to 1. We can assume that the given statement P of n is true for n equal to k, that is P of k, such that a power k is equal to a1 power k 0 0 0, a2 power k 0 0 0, a3 power k. This is P of k. This is our assumption value. Next, we can prove P of k plus 1 is true for n equal to k plus 1. P of n is true for n equal to k plus 1. Then for that we can consider P of k plus 1 such that a power k plus 1 can written as a power k into a power 1. That means a power k value already we know. A power 1 nothing but a. Then that is equal to a power k value is a1 power k 0 0 0, a2 power k 0 0 0, a3 power k into a value is a1 0 0 0, a2 0 0 0, a3. Then after multiplication, a1 power k into a1, a1 power k into a1 plus 0 plus 0. Next 0 plus 0 plus 0, again 0 plus 0 plus 0, 0 plus 0 plus 0. This is a2 power k into a2 first 0 plus 0, 0 plus 0 plus 0, 0 plus 0 plus 0, 0 plus 0 plus 0, and 0 plus 0 plus a3 power k into a3. This is our after multiplication matrices, that is equal to a1 power k into a1 power k plus 1 plus 0 plus 0 zeros, all zeros, 0. Similarly a2 power k plus 1 0 0 0, a3 power k plus 1. After comparing this matrix with P of n by substituting n equal to k plus 1, the matrix is true. Then therefore P of n is true for n equal to k plus 1. P of n is true for n equal to k plus 1. Hence, the final statement, hence by mathematical induction, P of n is true for all positive integral values of n. This is our first problem in the section 3. We will go to second problem in the same section. Next, second problem is if theta minus phi is equal to pi by 2, then show that matrix cos square theta into sin theta, cos theta into sin theta, sin square theta into cos square phi, cos phi into sin phi, cos phi into sin phi, sin square phi equal to 0. This is our given problem. In this we have to given one condition is that theta minus phi equal to pi by 2. By using this condition we can show these two matrices multiplication is equal to O. Then for that solution, first given condition, write down the given condition. Given condition is that theta minus phi equal to pi by 2. From this we can write theta equal to pi by 2 plus phi. This is our given condition. Next we can take LHS value, that is LHS equal to cos square theta, cos theta into sin theta, cos theta into sin theta, sin square theta into cos square phi, cos phi into sin phi, cos phi into sin phi, sin square phi. This is LHS value. We can multiply these two matrices, that is equal to, first multiply first row with first column, cos square theta into cos square phi, cos square theta into cos square phi plus cos theta sin theta into cos phi sin phi. Similarly, first row with second column, cos square theta into cos phi sin phi plus cos theta sin theta into sin square phi. Similarly, second row first column, cos theta sin theta into cos square phi plus sin square theta into cos phi sin phi. Second row second column, cos theta sin theta into cos phi sin phi plus sin square theta into sin square phi. This is our multiplied matrices. In this matrix we can substitute this condition. Substitute theta with pi by 2 plus phi. Replace theta with pi by 2 plus phi. Then that is equal to cos square theta means pi by 2 plus phi into cos square phi plus cos of pi by 2 plus phi sin of pi by 2 plus phi into cos phi sin phi. This is first element only. In second element, cos square theta means pi by 2 plus phi, cos phi sin phi plus cos of pi by 2 plus 5 into the remaining part, write down in the below, sine of pi by 2 plus 5 into sine square 5. All this is one element. Second, cos theta means cos of pi by 2 plus 5 sine of pi by 2 plus 5 cos square 5 plus sine square of pi by 2 plus 5 cos 5 sine 5. This is second element. And final element is cos of pi by 2 plus 5 sine of pi by 2 plus 5 into cos 5 sine 5 plus sine square of pi by 2 plus 5 into sine square of 5. This is final fourth element. Next, the calculation part is next. It is equal to, this is the before step. Here, cos square of pi by 2 plus 5. We know cos of 90 plus theta. That means pi by 2 plus theta. This is one of the formula. That is minus sine theta. This is one of the formula we can know in trigonometry by using this. Cos of pi by 2 plus theta. Here theta means 5 is minus sine theta. This is minus sine 5. Minus sine 5 whole square. Minus sine 5 whole square. Square is there. Then cos square 5 same, cos square 5 plus cos of pi by 2 plus 5 minus sine 5 sine of pi by 2, and the formula sine of pi by 2 plus theta value is that equal to cos 5, cos theta. That is cos 5. Cos 5 sine 5 common. Cos 5 sine 5. In the same way, cos square of pi by 2 plus theta minus sine 5 whole square. Cos 5 sine 5 plus cos 5 by 2 plus theta minus sine theta. Sorry, minus sine 5. Sine value cos 5 sine square 5. Cos of 5 by 2 5 by applying minus sine 5 into cos 5 into cos square 5 place of minus cos 5 whole square plus sine of plus cos 5 whole square into cos 5 into sine 5. Next, cos of 5 by 2 minus sine 5 into cos 5 into sine 5 plus cos 5 whole square into sine square 5. This is the calculation, that is equal to minus sine 5 whole square value is sine square 5 into cos square 5 plus into minus sine 5 into sine 5 sine square 5 into cos square 5. Similarly, minus sine value sine square 5 cos 5. This is sine square 5 cos 5 into sine 5 plus into minus sine 5 cos 5 sin square phi minus of sin phi cos phi into cos square phi plus cos square phi cos phi sin phi minus sin phi into minus sin into sin square phi cos into cos square phi plus cos square phi into sin square phi. This is here plus and minus, all plus and minus are cancelled. That is equal to 0, 0, 0, 0. This is that equal to matrix O. This is RHS. Therefore, LHS equal to RHS. Hence, the given statement is proved by using the condition theta minus phi equal to pi by 2.
Thanks for watching our video. For more videos, please like, share, subscribe to our channel and hit the bell icon.